All right, this is Unit 1, Part 3. It's on basic and inorganic chemistry. Okay, so what is matter? Anything that has a mass and occupies space. There are three states: solid, liquid, and gas. Solid has a definite shape and volume. Liquid has a definite volume but changes in shape depending upon what it's in. And gas has both changeable shape and volume. Energy is the capacity or ability to put work, to do work, or take matter, mass into and put it into motion. There are two types of energy: kinetic energy and potential energy. Kinetic is energy of some sort of action, something's happening, and potential energy is energy of position, stored energy. Energy stored within storage molecules like ATP, which is what the body uses. It's a organic molecule that the body produces as a energy store. So the different forms of energy, further forms of energy are chemical, electrical, mechanical, and electromagnetic. Chemical is in the bonds. So here we have a potential energy, chemical energy in the bonds that form the molecule ATP, adenosine triphosphate. Electrical energy comes from the movement of charged particles. Mechanical is, I'm sorry I'm reading this, but these are just fundamental basics. I'm not going to add or subtract anything from these notes, many of these notes really, especially at the beginning here. Mechanical energy is directly involved in moving matter. Electromagnetic energy is energy that travels in waves. It can be visible, ultraviolet, X-ray. Visible light spectrum is what you can see. The others are not visible to the human eye. Infrared is another one. Now energy can be converted from one form to another fairly easily, although it is important to realize that during these conversions, none of them are 100% efficient. In other words, the full amount of energy in the first form, when it's being converted to another form, is not present in the second, in the end form of energy produced. There's always some loss of energy, and that energy in biological, in many systems, is lost as heat. Certainly in biological systems, it's lost as heat. Lost is not the right term to use necessarily when we're talking about a biological organism, because heat is important in a warm-blooded organism. Matter is composed of atoms. These are the building blocks for each of the elements. The atoms form into elements, the periodic table of elements. These are each unique substances with characteristic, with the typical characteristics. They cannot be broken down by ordinary chemical means. The atomic symbol for each of the elements is a 1 or 2 letter name, which is a chemical abbreviation or shorthand for each of the elements. Hydrogen, for example, is H, gold is AU, lead is PB, sodium is Na, Okay, and here is the periodic table of elements showing all of the elements, and all of these make up all of the matter in our world. Each different element has unique physical and chemical properties. The physical properties can be detected with our senses and are measurable, and the chemical properties pertain to the way the atoms interact with each other. The major elements, although there are many others, but the four major elements that make up more than 96% of the body include oxygen, carbon, hydrogen, and nitrogen, and their abbreviated symbols are beside that, OCHN. This is a table which I suppose you could, read it. You don't have to know the exact percentages, but you can see that most of the body is made up of oxygen, carbon, hydrogen, and nitrogen. There are lesser trace elements, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, iron. You should be able to recognize the symbols for each of these. I'll use them later on in the course, certainly. These are lesser elements that make up, roughly 4%, and that there are trace elements required in tiny, tiny amounts, but they are key. They're typically found as part of enzymes and are often required, absolutely required as cofactors for enzyme activity. Again, a table showing percentages, tiny percentages. Don't even think of memorizing these percentages. Just know that they're small. Know that the symbols for these, and be familiar with some sort of basic function for each of these. The calcium is found in bones. It's also important for other functions. Sulfur is part of proteins. It makes up a part of 2 of the 20 different amino acids that go to form proteins. Iron is a required component in hemoglobin, and there actually are many iron-containing molecules in the body. Most are enzymes. The trace elements, as I said, are tiny in amount and often involved as part of enzymes and are required for their enzyme activity. Okay, again, pure high school, simple high school stuff. Even, I don't know, I may have learned it even before high school for all I can remember that far back. Each atom has a nucleus, and inside the nucleus are neutrons and protons. The neutrons do not have a charge. They have an atomic mass unit of 1. Protons have a charge, positive charge, and an atomic mass unit of 1. Electrons, which have a tiny mass, are found orbiting in a cloud outside of the nucleus, outside of the atomic nucleus. There are 2 major models of atoms that are typically used to explain the structure of an atom: the planetary model and the orbital model. In the planetary model, the electrons are shown moving around the nucleus in fixed circular orbits. And this is a model that lends itself well towards explaining how atoms can interact with each other to form bonds. The orbital model just shows that there's a somewhat, amorphous, undetermined region around the nucleus where the electrons are moving. It's probably more accurate, somewhat more accurate than the planetary model, but it doesn't lend itself to, using it to illustrate, to explain interactions between different atoms. So here you see the nucleus. This is helium having 2 protons and 2 neutrons. It's a small molecule. It's inert because the 2 protons cancel out the charge of the 2 electrons, so it has no net charge, obviously, here. This is the planetary model showing orbiting electrons, and this is the orbital model showing that they're really in a cloud. I mean, they move around incredibly quickly around. They're in this area going around the nucleus, and they are within the outside of the nucleus, and they spend most of their time at a certain distance from the nucleus, but not always. So it's difficult to determine exactly at any one moment where precisely they are. And that's what's shown by this electron cloud model. Elements are defined according to their certain characteristics, including atomic number, which is equal to the number of protons, the mass number, which is equal to the mass of protons plus neutrons. The atomic weight is the average of all the different isotopes of a element that you can find. An isotope these are atoms with the same number of protons but a different number of neutrons. They're going to have similar, not identical characteristics to each other. So you find naturally isotopes for many of the elements. You find a number of different two or more isotopes, which vary from each other not in proton number but in neutron numbers. The atomic weight is just the average mass of all of them. It takes into account I believe takes into account the prevalence of each type. Radioisotopes are atoms that can undergo a spontaneous decay or change in their energy content. They can release a lot of energy and change in their and that energy released is called radioactivity. So an isotope is not radioactive, but radioisotopes are. Okay, so here we have three different elements. You see hydrogen, helium, and lithium. And the atomic number is 1, 2, and 3. Hydrogen having 1 proton, 1 electron. Helium, 1 proton, 2 protons, 2 electrons, and 2 neutrons. There are no neutrons in hydrogen. Let me see now. Yeah, and lithium. Let's move on. There are 3 common isotopes of hydrogen that are found. Remember, isotopes will vary from each other in their neutron numbers. Most hydrogen, the vast majority of hydrogen in nature, does not have a neutron. Deuterium has 1 neutron, and therefore is heavier than hydrogen. And in fact, water, H2O, made using deuterium as opposed to hydrogen is what is called heavy water for obvious reasons. Tritium is actually it's an isotope which is radioactive. It's releasing radioactivity, so it's a radioisotope. It has 2 neutrons, 1 proton, 1 electron. So it's significantly heavier. Okay, now people use these 2 terms, and the most commonly used term that you'll hear, and what I typically use and what you'll see in most textbooks, most sources, are molecules, as opposed to talking about compounds. Molecule is the smallest particle of a substance that keeps its particular chemical and physical properties. Remember, when you construct, if atoms are brought together to form stable covalent bonds, tight bonds with each other, and they form a stable type of molecule, they're held together, and they have a particular chemical and physical characteristic properties. So if you have 2 or more atoms, either the same or more, and they're held together by chemical forces, then this is a molecule. So 2 or more atoms of the same or different elements held together by chemical bonding. Stable, strong chemical bonding. And when it says chemical bonding, I would basically include here covalent bonding and ionic bonding. A compound is subtly different in its frankly, your book uses compound. They form a distinction, but people just use the word molecule. So compound, 2 or more different kinds of atoms chemically bonded together. I don't see that it's that much different. An additional point, but I would say it applies to molecules, cannot be separated. All compounds are homogeneous. Yeah, if it's single compound, I use molecules, books use molecules. I taught biochemistry for years. Molecules. In living biological systems, they talk about molecules. Stick with molecules. Okay, if two or more materials, anything made of two different types of elements or two different molecules, whatever, if they are brought together physically but are not bonded together by chemical bonding, then it's a mixture. It's a mixture of two separate things. They are, yes, they're mixed to varying degrees, either crudely, you pour a can of blue paint into, well, it's just an example, visual example. You pour a can of a blue colored molecule into a can of white colored molecule, and you see big swirls. Or you could mix it up physically, and it would be a light blue. But if it's not bonded chemically, they are not actually forming into something new, so it's a mixture. If you get a homogeneous mixture where one molecule is dissolved into the other, then it's a solution, and the substance that is dissolving is called the solvent, and the solute is what's dissolved into it. These are subtleties that we don't talk about typically. We talk about solutions. A solution of sodium chloride is NaCl. Ionic solution, salt solution. For example, a glucose solution, where you're putting glucose in the water, salt solution. And the typical, in biological systems, the typical solvent is water. We are water-based organisms. Our solvent that we use is water. Concentration of solutions is expressed in percent, parts per 100, or in molarity, moles per liter. A mole is equal to the atomic or molecular weight in grams. So a 1 mole solution of sodium chloride, or having molarity, 1 molar would have 1 mole per liter. So you look at what the molecular weight is of sodium chloride, and if you express it in grams, that's how many grams are in that liter of liquid. Totals. When things are mixed together, this would apply, I guess, to pharmacological agents. When things are mixed together so that it's a heterogeneous mix, which is stable in that one doesn't settle out from the other, but it's still, they're not forming chemical bonds with each other. It's called a colloid or an emulsion. A suspension is a heterogeneous mix, well mixed up with any visible solids tend to settle out in that suspension. It's suspended in, and if you leave it, the visible solids will settle out. It's like having a suspension of earth, sand in water, for example. Okay, mixtures, no chemical bonding, I already told you that. Most mixtures can therefore be separated using physical means, as opposed, you don't use chemical methods to separate out the constituents that make up a mixture. They can be separated physically. They could be heterogeneous or homogeneous, well mixed up, or poorly mixed. A compound, however, and we go back to compounds essentially being molecules, cannot be separated by physical means. You have chemical bonding between the elements within it, between the elements or atoms within it. It's a homogeneous a material, chemically bound to each other. You cannot separate it by chemical means. Okay, here we get into something that's, say, more scientific, less definition and more talking about interactions between molecules or atoms. Remember, in the orbital model, we have these orbits or shells, electrons orbiting around the nucleus of an atom. So these orbits are called electron shells, and they reflect the energy level. The higher, further out it is, the higher amount of energy it has. And bonds will be formed using the outermost orbit of orbiting electrons. So bonds between two different atoms will form using the electrons in their outermost orbit, their highest actual energy level electrons at the outside. And that's what's these different orbits or shells are called valence shells. And the outermost, as I said, contain the most chemically active electrons. There is, in terms of these orbits or valence shells, a rule called the octet rule. Except for the very innermost orbiting electrons, where you have two electrons in a full first in a first shell that's full, every other orbit or shell further away from the nucleus will need 8 electrons to be full. And as I said before, the different atoms will interact with each other by gaining or losing, sharing electrons, so that, well, I didn't say this before, but the outermost shell is the one that's interacting between different atoms, and the atoms interact, and they will either pick up an electron from another atom, the outermost orbit or valence shell of the other atom, or they will donate one, lose one to that other, or they will share it between themselves. And I think the next slide should be a diagram showing, well, it shows a helium atom, which has a proton and 2 electrons, and it shows neon. Has two protons and 2 electrons, and neon, it's showing the nucleus as a single sphere. Okay, that's not a proton. That's the in the middle there. That's the in the middle here. That's the nucleus, and it contains 10 protons. And the first valence shell has 2 electrons. And then the outermost has 8 electrons, and because it has a full complement of 8 electrons in that shell, it is not particularly reactive. In fact, neon is considered to be an inert gas. Okay. These examples here do not have full outer electron valence shells, and therefore are potentially reactive with other atoms. They could gain or lose or share electrons with some other atom, and therefore these are considered to be chemically reactive elements. Their outermost energy valence shell or energy level orbit is not fully occupied. Here with hydrogen it's only 1. Here with carbon you have 4, not 8. Here with oxygen you have 6 electrons in the outermost shell, not 8. And with sodium you have 1. Okay. When you look at molecules made of atoms, the atoms can be held together in different ways. By different types of bonds, all right? And when I said chemical bonds, that includes each of these three types of bonds: ionic, covalent, and hydrogen bonding. But I just want to point out to you that hydrogen bonding is extremely weak and normally fairly fleeting. It doesn't hold things together very um, strongly at all. But there are some molecules out there that have so many hydrogen bonds in them. They're fairly large molecules that have many, many, many hydrogen bonds between different parts, and so they become stable just from not from the strength of an individual hydrogen bond, but because they have so many of these hydrogen bonds. But when we look at many molecules in nature, you have ionic bonding, which is quite strong, and covalent bonding, which is particularly strong. Let's go into each type more in more detail. Ionic bonds are formed as a result of a gain or loss of electrons, not a sharing, a gain or a loss. If the molecule is an anion, if the atom is an anion and the molecule is an anion, it means it's gained one or more electrons. Because electrons are negatively charged, it will therefore be negatively charged. And cation, if a molecular atom is cation, it will have lost one or more electrons, so it's positively charged. And anions and cations interact. The cation gains an electron from, the cation loses an electron to the anion, and the cation loses an electron to the anion gains an electron from the cation. There's a donation here. If this is a electron, it's gone over to here, from the cation to the anion, and therefore you have negatively charged and positively charged molecule or atom, and therefore they will be attracted to each other because of the attractive interactive force of negative and positive charges. Ionic bonds are different from ionic bonds form due to transferring of one or more electrons, as I said on the previous slide. And they will form crystals instead of individual molecules, unless they're in solution, then you don't see them. They will form crystallized structures. And a very good example, a typical example and quite relevant to living organisms is sodium chloride in solution, NaCl. When sodium, Na, interacts with chlorine, Cl, you get a transfer of that single electron that's in the outer orbit of the sodium. It gets transferred over to the chlorine, which has 7 electrons in its outermost shell, and therefore becomes stable once it gets that 8th one from the sodium. And the sodium in turn becomes more stable because it has given up an electron, that single electron in its outermost shell. And in this way they form a stable interaction, which is in fact an ionic bond. That is an ionic bond. The shifting over of the electron to spend time with the chlorine atom forms this attraction because it results in a charge of a positive charge in the sodium and a negative charge in the chlorine. Therefore you get sodium chloride interacting with each other through an ionic bond. That's an ionic attraction. And as I said, they'll form a crystalline structure. They'll arrange themselves very nicely. The molecules will arrange themselves. The atoms will arrange themselves very nicely, uniformly together. In the case of sodium chloride, the most stable interaction shape will be into this cube-like shape, which is why crystals of sodium chloride are cube-shaped. But if we're talking about some other two other completely different elements that can form ionic bonding. They'll interact in a different way, and you'll get a different shape. And as the crystal grows, it continues to retain that shape as the atoms pack in and form ionic bonding with each other, and they get bigger and bigger and bigger. So when you look at a naturally formed crystal, if it's, in this case, sodium chloride, it'll be cubed. No matter how big it gets, it'll retain that cubic form, that cubed shape. And so some other elements forming a ionic bonding with each other that has crystallized because it's come out of solution, so it's solid crystal, will retain a particular shape. And if you look at the natural form of the crystal, it's easy to identify what it is because, you know, it's known what shape they take. Now, hydrogen bonding is important. Ionic bonding is important, but particularly of importance and need for you to understand are covalent bonds. This is formed by the sharing, not gaining or loss of electrons, but sharing of two or more electrons between two or more atoms or molecules. And this forms a covalent, this will result in the formation of a covalent bond, which is extremely stable, typically very stable, and it requires chemical means to break and produces a molecule. So here you see 4 hydrogen atoms interacting with carbon. Carbon has 4 electrons in its outermost shell, so it's, well, you could look at it 2 ways. It's 4 short or has 4 too many. In this case, we're looking at it as having 4 less than a complete octet, so it's it'll be stable if it can share 4 more electrons, and these get shared from each of these hydrogens, and you get this stable forming structure of CH4, which is methane. And in this way, the molecule, and this is the more another chemical way of depicting the molecule here. Each single line represents the sharing of 2 electrons between these atoms, between this carbon and between this carbon and this hydrogen. There's a sharing of 1 electron from each, and this one, and then this one, and this one. So 4 electrons are shared with the carbon, and you get a stable methane molecule. Now, that was a single bond indicated in this diagram before, the diagram of methane, by single lines. Here you have 2 lines. That's a double bond. That means that instead of 2 electrons being shared, there are 4 electrons being shared in a double bond. And that can happen with, in this example, oxygen. Oxygen has 6 electrons in its outermost valence shell or orbit. And this second one also has 6. Now, when they interact with each other, if they share 4, then you end up, these 4 electrons are spending time, some of the time with this oxygen nucleus here, and some of the time with this oxygen nucleus here. And so much so going back and forth essentially that you can't distinguish, and forms the 4 plus these other 4 forms a stable outer orbit containing 8, and the rest of the time alternatively is forming, sharing with this one here, these 4 here in this outer shell, so 8, and therefore is forming a stable double bond to form molecular oxygen, which is, of course, O2. And that's what we have in our atmosphere. About 20–21% of the atmospheric gas is oxygen. And remember that air is a mixture of gases. It is not some sort of there is no such thing as a molecule of air. Air is a mixture of different kinds of gases that each retain their own physical chemical properties. There's oxygen, nitrogen, a little bit of carbon dioxide, some water vapor. Okay, so this is a molecule of oxygen forming stable double covalent bond and the stable O2 molecule. Oxygen itself on its own, a single oxygen atom, is not very stable at all. It's very reactive. It'll quickly react with other types of molecules because of this incomplete outer shell. Triple bond, triple covalent bond, shown in drawing as 3 lines here, is shown with nitrogen gas, again a major component of the air. In fact, about 80% of the air mixture is nitrogen, and we breathe it in and put it and then breathe it out. It doesn't. We don't take it into our body, and that's there because in order to form if when you look at the nitrogen, a single nitrogen atom, it has 5 electrons in its outermost valence shell, and when you put 2 of these together and they share 6, 6 plus 2 is 8. So these 6 and these 2 make 8, and these 6 again in the middle, and these 2 make 8. So that's a stable molecule of nitrogen that's covalently triple bonded to form a stable molecule of nitrogen. Happens to be a gas. All right, we'll stop here. This is the end of Unit 1, Part 3.